Hello everyone, welcome to the rate and equilibrium video lesson. Let's begin by talking about chemical reaction rate. So in order for a reaction to occur, the molecules of reactant have to crash into each other. And if they crash into each other under the right conditions, we end up with what's known as an effective collision. Effective collisions are where we end up breaking bonds so that we can form new bonds. So what conditions do we have to satisfy in order for the bonds to break? Well, we need sufficient energy of collision. So these molecules have to slam together hard enough to shatter those bonds apart in order to form new bonds. If the collision isn't hard enough, they simply bounce off each other and no reaction occurs. And we also need the right orientation. If these things crash into each other at the wrong angle, they can't get the bonds to break and they can't form new bonds. And so again, we'll get no reaction. So it's actually only a tiny percent of collisions that are effective. Only a small number of them will satisfy these two conditions and be able to break bonds and cause a chemical reaction to occur. So one of the things that's required, we mentioned we have to break the bonds. And so the energy required to break the bonds is known as the activation energy. And this activation energy varies from reaction to reaction. If we have strong bonds, then we need a lot of energy to activate things, a lot of energy to break those bonds. And if they have weak bonds, then this might be a much smaller value. So any sort of factors that will affect the collisions in a chemical reaction will also affect the rate. So first up we have concentration. As we increase concentration, we have more particles in the same amount of space. The particles are closer together. They're going to crash into each other more often. And so because we have this higher number of collisions, when our concentration goes up, our reaction is going to get faster because we're going to have more collisions and more bonds breaking essentially. Temperature has a very dramatic effect, and so with temperature it affects our rate in two ways. So at a higher temperature we have faster moving particles. And these faster moving particles are going to collide with each other more times per second, so we'll have more collisions per second, but we're also going to have higher energy collisions. Those collisions are going to be more likely to break bonds and smash things apart. And then finally, catalysts are going to speed up our rate of reaction. They do this by bonding to our reactants and weakening their bonds. And when these bonds are weaker, they're more likely to break in each collision. So this is sort of a unique one here. It doesn't give us more collisions or higher energy collisions, but it does increase the probability that our collision will be effective, which actually very dramatically increases our rate of reaction. I know a lot of you guys are interested in the health fields, and we call catalysts in biochemistry enzymes. And enzymes are tremendously important for getting all the reactions in our body to work properly. So here's a diagram of how the catalyst works. We have our sort of energy we have to input without the catalyst. Our bonds are strong, so we need a high energy collision. So in other words, our collision probably isn't going to have enough energy to break our bonds. It's not likely to be effective. We have this high activation energy required. Now if our catalyst binds to our reactants, we lower activation energy because we weaken those bonds. And so now our collision is actually far more likely to result in reactions. So we're going to have way more effective collisions per second and a dramatic increase in our rate of reaction. So if you could now pause the video, please complete questions 1 through 3 in the activity. Welcome back, everyone. Let's switch gears and talk about reversible reactions. So some reactions are reversible, meaning they can go in both directions, and other reactions aren't. So reactions that are reversible are reactants can combine with each other to form products, but then simultaneously the products actually decompose back into the reactants. This type of thing tends to happen if our reactants are relatively similar in stability or potential energy to our products. That's what allows our reaction to go both directions. If the product is much more stable, much lower in energy, then our reaction will not go in reverse. So this is why you never see like carbon dioxide and water magically recombine to reform gasoline or firewood when you burn it, things like that. Only certain reactions have this ability to go in both directions, but these types of reactions are actually extremely important in biochemistry. So any reversible reaction, if we leave it sitting long enough, is going to reach this state of equilibrium. So what happens here? Well, our initial rate in our forward direction starts out high, but it's going to decrease. And the reason for this is our concentration of reactants goes down over time. And so our reactions get slower and slower. And then our rate in the reverse direction is actually going to increase. As we make more product, that product's actually the reactant for the reaction in the reverse direction. So our rate in our forward direction is going to increase. And eventually these rates are going to match each other and cancel each other out. And this is when we reach our state of equilibrium. So once we reach equilibrium, our reaction hasn't stopped. It's just proceeding at equal rates in each direction. So our concentrations cease changing. One of the important skills you're going to want to learn in this chapter is how to write equilibrium expressions. And they're pretty simple to do. There's just 3 steps you have to remember. Number 1, solids and liquids are left out of the expression, and gases and aqueous materials are included in the expression. How do you know what state something is? Well, remember these little letters in the parentheses? Those tell us the states. Next up, we put our products over our reactants. And then finally, coefficients are going to become exponents in our equilibrium expression. So in this equation here, we put our products on top. Everything's gases, so everything's included. We don't have any solids or liquids to leave out. So we're going to say Kc, it's called our equilibrium constant, more on that later, equals our concentration of our products over our concentration of reactants. These brackets mean concentration in molarity. And our coefficients become our exponents in our equation here. And here we have another example. This one we have some solid components, so we write our equilibrium expression. And so we leave these solids out, and our equilibrium expression actually ends up being quite simple. It's just Kc equals concentration of CO2 times concentration of H2O. Our coefficients are all 1 here, and the solids are left out of the expression. So what does this K value mean? Well, it talks about what sort of balance we favor when we reach equilibrium. If we have a large value of K, meaning much, much greater than 1, that means we're going to have more products to equilibrium than reactants. If our value of K is relatively close to 1, then that means that we're going to have relatively similar concentrations of reactants and products. And then finally, if we have a small value of K, that means we're going to have more reactants than products at equilibrium. And a small value of K can never be negative, but we're talking about a very tiny decimal number here. It's often expressed in scientific notation. These will have negative exponents as their power of 10, and these will often have positive exponents for their power of 10. So please pause the video and complete questions 4 through 6. Welcome back, everybody. One of the things that you'll be asked to do with these equilibrium expressions is to calculate equilibrium constants. So here we have an example problem where we're asked to calculate our value of Kc, and we're given some equilibrium concentrations. Our first step is going to be to take our equation, which is balanced, always double check your equations are balanced, and write an equilibrium expression. So everything's gaseous, so everything's included. We put products over reactants. And our exponent here, our coefficient here becomes an exponent. Next, we're actually going to plug numbers in. So we're going to stick in here. Here's our concentration of our hydrogen iodide. So that's going to be 1.47, and we square that because of the 2 in our equation. And then we plug in our concentrations for our iodine and our hydrogen. And if we crunch all our numbers, we come out with a value of 54. So our value of Kc here is 54. We have a second example here, and now we're asked to calculate the Kc for the reaction below, and we're given the concentrations. And so once again, we want to write our equilibrium expression. So products over reactants, solids and liquids are left out, and coefficients become exponents. There's our equilibrium expression. Now we're going to plug in our concentration. So here's our CO concentration, boom, plug it in right there. H2, boom, plug that in there. Here's our CH4, and then we plug in our water right here. And now if we crunch all our numbers, we end up with a value of 0.26. So please pause the video and complete question number 7. Welcome back, everyone. Let's talk about another way we can use these equilibrium expressions. We can also use them to calculate equilibrium concentration. So in a problem of this type, you'll be given the equilibrium constant, it's presented right here, along with all the concentrations but 1. So here in our equation we have phosphorus pentachloride decomposing to form phosphorus trichloride and chlorine gas. And so we plug everything into our equilibrium expression here. We have no exponents because everything's just got a coefficient of 1 in the balanced equation. We have no solids or liquids to leave out, so there's our expression. And now we're going to plunk our numbers in there. Well, actually, before we do that, let's rearrange. So we rearrange to solve for the missing concentration. And if you're fuzzy on your algebra, I would highly recommend checking out the LSC. Those math tutors over there would be happy to help you with this type of substitution. And now we're going to plunk in our numbers into the equation. There's our Kc, and there's the concentrations we're given. And we end up with a molarity of 0.24. So that's our missing concentration right there. And we have a second problem right here that's very similar. We're given, again, our equilibrium constant. We're given all the concentrations but one, and we're asked to find that missing concentration. So we want to find the concentration of the bromine here. So we generate first our equilibrium expression. No solids or liquids to leave out. Products over reactants. Coefficients become exponents. Boom, there it is. And now we're going to rearrange to solve for our missing concentration. Our concentration of bromine is going to equal our concentration of NOBr times our equilibrium constant divided by our concentration of NO squared. And so now we plug in our numbers. So here's our concentration of our chemicals as well as our equilibrium constant, and our missing molarity is 0.78. So I'd like you to pause the video and please complete question number 8. And once you finish question number 8, you should head on over to the discussion board and participate with your classmates. Thanks. Bye.